Here's a good kinetics problem. Let's deal with it. It starts with tertiary butyl chloride, but let's take a little side trip to tertiary in organic chemistry. It's an interesting term. First of all, butyl in carbon means that you've got 4 carbons. If you can see here, we have 3 carbons and then 1 more, so that's 4. So indeed, we have 4 carbons. So you have 4 carbons and a chloride. But what does this tertiary mean? Well, there's primary, secondary, and tertiary carbon compounds, and this is tertiary butyl carbon. And notice here they've got a picture of it with our chlorine, a carbon here, and then at the end of each one of these there's another carbon. So we have our 4 carbons. But see, when they've got a bottle of it here with as a liquid, it's shown as a T. That can help you remember tertiary. They mean the central carbon that you have is attached to 3 other carbons. The central carbon is attached to a carbon, carbon, and carbon. And then this 4th bond, which you could possibly have, isn't attached to a carbon. Hence 3 being tertiary. A quaternary would end up having a 4th carbon attached to our central. So that's the terminology: primary, secondary, tertiary, and quaternary. A tough one to pronounce, and I probably mispronounced it. But back to our problem. Here we've got our chloride reacting in a basic solution. Hydroxides are basic, and it turns into an alcohol. Bet that this is called tertiary butyl alcohol, or tert-butyl alcohol. Its reaction occurs in a series of steps that is pretty typical. In step 1, we've got our tert-butyl chloride decomposing, probably a photon hitting it or some heat, and breaking up to make a carbon cation, or a tert-but cation. And then that cation reacts with hydroxide quickly to make the alcohol. Now, our rule in reaction kinetics is that when we put together a rate law for what happens, we look for the slow step. And if the slow step is the first one, it's pretty easy. All you have to worry about is the reactants in the first step of the slow step. So here it is: slow step, reactant. So the exponents in this rate law would be pretty straightforward. Here I've got it written now. The reactants in the slowest step of a reaction mechanism will determine the overall reaction. Now there's some complications when it's the second step and we've got an equilibrium, but this is a simple one, so we'll just deal with that. So we just have one reactant. Therefore, our rate law is pretty simple. Well, if you can call any rate law simple. The rate is equal to our rate constant times the concentration of this stuff. The tert-butyl chloride is the only thing that's important in determining how quickly this reaction goes. The speed of the reaction is dependent upon this molar concentration that we have. Let's go on to B. We figured out the rate law, and that's what this is, the rate law. This is the law that tells you how fast this reaction is going to go. Will it take a fraction of a second, or will it take days or years? Well, that's what this constant is about. So let's go a little bit further up now. In order to confirm the order of the reaction and the mechanism, now there's this theory, we got this theoretically from the steps in the reaction. The experiment is done, and they measured the formation of the tert-butyl alcohol using different concentrations of the tert-butyl chloride. Organic chemistry, I love those names. What initial rate would confirm the proposed reaction mechanism? Okay, well, let's look here. We've got the first experiment, 3/10 molar tert-butyl chloride and 3/10 molar hydroxide. And this is how quickly we form the stuff. Molars per second, that's speed. So it's pretty slow, 0.00004 molar for every second. Now they changed the concentration of the tert-butyl alcohol, and we increased it, and we noticed that the rate increases too, which is what you'd expect from this reaction. Now to make this a little bit clearer, I always like to have these exponents in the same power, so you can see what's happening better. So I've rewritten this table, and what I've done is I've changed that 1.2 times 10 to the negative 4 to 12 times 10 to the negative 5. So these are both times 10 to the negative 5. So we doubled the tert-butyl chloride and the rate of the formation of the alcohol doubled too. Well, that makes sense. If we double this concentration, the rate doubles. This rate law does make sense. So we've confirmed the mechanism that was proposed for this reaction. We've got experimental proof. Now we could then do another experiment where we have 6/10 molar tert-butyl chloride, 6/10 molar tert-butyl chloride, and now we double the hydroxide. But according to this rate law, the hydroxide doesn't matter. That's because it's the fast step. The hydroxide is waiting for the chloride. And as soon as it appears, it takes care of it. So we'd expect that the rate for this reaction wouldn't be changed. That would be our expectation, that it's still going to be 1.2. So what? You increase the hydroxide. Nobody's concerned about the hydroxide. Everybody's waiting for the chloride. Based on the experimental data and the reaction mechanism, what is the rate constant and unit for this reaction at this temperature? We want to find out what K is, the rate constant. We found the rate law expression. Now we want to find the K. All we have to do is know the rate and the concentration of the chloride. So we could take any one of these trials, plug in the numbers, and solve for K. I'm going to use trial 1. You could use trial 2 if you want. Try it, and you're going to get the same answer, or very, very close to it. Plugging in, we've got our rate law. Forget the hydroxide. That makes us easy. That's good. You love these first-order reactions. We know what the rate is. Here's our rate. 6 times 10 to the negative 4. Now, its units are molar per second. How many molar per second are we producing in this case? And we're going to take our 3/10 molar chloride, because at this concentration of the tert-butyl chloride, we get this speed. Your algebra sheet good enough to solve for this. I've got it set up here so you can see the algebra, but you could probably have done this on your calculator and in your head without having to write that. So I've got my calculator, and I'll just do this 6-second function e negative 5 divided by the simple 0.3, 2 times 10 to the negative 4. That is the K that we get. 2 times raised 10 to the negative 4. Always on FRQs, when you find out stuff about rate laws, you have to show the unit. Sometimes you get 1 point just for the unit. I mean, you can get this number wrong and then get a point if you've got the unit right. Well, in any first order overall reaction, if you have a rate constant, the rate constant multiplied by the concentration should give you molar per second. And therefore, the unit for any first overall reaction is per second, assuming that we have seconds here. It could be per minute, per hour, per millennia, as long as it is just per second. Because when we multiply per second times molar, we get molar per second. That's our unit. So remember that units are worth a point. Like I say, you could do this math wrong, or even not even do the math. Guess a number and write per second and probably get a point on an FRQ. But we can't leave this problem without talking about tert-butyl alcohol. So here's something on tert-butyl. Tert-butyl alcohol itself is an interesting alcohol. It's a solid at room temperature, but it melts pretty easily. They say it has a camphor-like odor that's almost sort of like a piney odor, and it dissolves nicely in water, which is what you'd expect. It's a small molecules. It's got an OH. And generally, it's surprisingly, it's been found in beer and even in chickpeas, which sort of surprises me. Commercially, it's used in paint removers. It's a pretty decent solvent. It even increases the octane numbers of gasoline. So tert-butyl alcohol, and you know a reaction that makes it now. And even know what tert means. That's interesting. Okay, there's our question. And some.